Okay guys, so now we're moving into chapter 16, so go ahead and take a screenshot of this page. We honestly didn't grab too many from chapter 16, which isn't a big deal. He gave you guys a lot on Canvas, and these are ones that you may or may not have seen on Canvas, but yeah, these are kind of like the harder ones that you would see from 16. Okay. Once again, we start out with some naming, and then we talk about stereoisomers, which I know everybody had questions about, so we will go over these. So, let's go ahead and start with the first one. We're asking for the correct Iupac name for the following compound. So, once again, like what I like to do is to count out our longest carbon chain. So, I go 1, 2, 3, 4, 5, 6, 7, 8. So our longest chain is a octane. Yeah, that's how you spell that. An octane. So we know anything that does not have the word octane at the end is going to be out. So we know A, D, and E are out. So now we're stuck between B and C. So we see that 4 is going to have the ketone. Both of these do have 4 as the ketone. And then 6 isopropyl. So it's saying this is an isopropyl group. But remember that we wouldn't really split it up to call one part an isopropyl if we're going to name the whole chain an octanone. That was a little confusing, but basically, since we're including these 3 carbons here, we're not going to be able to call this part an isopropyl. So basically, these carbons are included in the base chain of the octane. So we would not call it an isopropyl. We would instead just call it an octanone with a methyl. So it will be 7-methyl-4-octanone. All right, let's go on to the next one. What is the Iupac name for this compound here? So this is where you kind of have to have that sheet that Dr. West posts on Canvas when it comes to naming and the priority groups. I mean, the functional group priority. That is what I meant to say. So we do know that we are going to want our longest base chain, so let's go ahead and count that out. 1, 2, 3, 4. That was a horrible 4. 4, 5, 6. So we know this thing is going to be a hexane. So anything that does not say hexane in the name, you can cross out. That is basically just D. So now we can kind of go through them. So we know that our phenyl is actually going to have priority over our ketone and then our alcohol. So we want this guy here, our phenyl, to have the lowest number. So phenyl on the 2 will give it its lowest number. So now we need to see which ones will give us 2 phenyl. So A does not, it gives us a 5 phenyl. C doesn't because it gives us a 5 phenyl as well. So now we're stuck between B and E. So B does have the 5 being a hydroxy, and then it also has our 3 being a ketone. But we wouldn't call it a keto. We will just add it to the end name. So 3-hexanone. So that is why B is going to be our answer for this one. So definitely just review that functional group priority list. I can show it to you guys really quick. Let me pull up Canvas. If you go to his page, underneath modules, it is underneath additional lecture material, and it is functional group priorities. And right here, he gives you the ending as a highest priority group, and he kind of puts it in a nice, neat little sheet for you guys. So definitely know this and remember these. Okay. And I kind of lied, guys. I'm sorry. So as you guys can see, the ketone has the N. So ketone is going to have a higher priority than our benzene and then our alcohol. So that is why our ketone is given the ending. So basically, since our ketone is number 1, ketone gets number 1 priority. and then comes our alcohol with the number 2 priority, and then this guy is our number 3 priority. So whichever one has the number 1 priority is going to be our end name, so anything that has the -one at the end is going to be our answer. So it could be B or C if we chose between these two. But then remember, we would want our numbers to have the lowest number chain, well, the lowest number of substituent. So if you look between C and B, this one has 2, 5, 4 versus B that has 5, 2, 3. So because of this difference, we are going to choose B over C. I hope that makes sense. I'm sorry I mixed you guys up a little bit. But definitely, as you guys can see, I need to review my functional groups as well. So go ahead and definitely know that chart. Okay. So here's the question that everybody asks about. It's regarding stereoisomers. So it's basically, if you guys remember from Orgo 1, there were things called stereoisomers. A stereoisomer is basically, they could be enantiomers or they could be diastereomers. Those are basically what our stereoisomers are. And so when we're looking at this, okay, it does say recordings in progress. We want to look at which one we can use as stereoisomers, meaning they could be diastereomers or enantiomers. So I'm just going to give you guys the answer to this and then explain the answer, so hopefully it makes more sense that way instead. So the answer for this is A. This is really weird because it says the hydrazone of a butanone. So what it's asking you to do is draw out a butanone, treat it with a hydrazine, and then get the end product of a hydrazone. So we are going to start out with a butanone. This is how I'm going to draw my butanone. It's just any butane with a ketone on it. And then we are going to be reacting it with H2. Basically 2 NH2s bonded to each other, and this is our hydrazine. Rosemary taught it a little bit differently. I will show you guys my shortcut for these guys. You do not need to use my shortcut if it confuses you, but for the people who have been attending my SI sessions, some of them found it useful. So what I do is this. I take one of the nitrogens, only one of the nitrogens. I scribble out its hydrogens. I then cut off the head of our double bond. So I cut off the head here, and I say I don't want you anymore. And then I just paste on whatever we have left over. So the NH2 that is left over is what we put on the double bond. That is my cleave and paste method. If it works for you, it works for you. If it doesn't, feel free to use Rosemary's method. But this is just kind of how I learned it, or how I have come to learn it to make it easier. So this is a hydrazone. Cool, we have a hydrazone, but what does that have to do with stereoisomers? So notice how we have two of the same group. We have both NH2s. We could have chosen either NH2 to use to put onto this guy. So we could have ended up with this hydrazone where we chose the first nitrogen to react with, or we could run the same method, but instead scribble out the H's of the second nitrogen, cut off the top, scribble it out, and we could have formed this instead. So notice how they basically look like the same molecule, right? But because of the orientation difference, where we use the nitrogen over here, then the NH2 is on this side, basically we use the other nitrogen and we have an NH2 on the other side. So these are called stereoisomers. They literally have the same amount of everything, just they're different arrangement. I'm sorry if that didn't really make a whole lot of sense, but hopefully it'll make more sense as the exam comes up. If you want me to kind of draw it out like this, where we have this, I could draw it out like this if it makes more sense. So then you guys can kind of see that we now have the nitrogen on this side instead, and then it's two hydrogens. But basically it's the same thing, and this is what they mean by stereoisomers. Basically, they're the same compound, same composition, it's just that we used one nitrogen over the other nitrogen for our synthesis. Okay, So hopefully that clears up that confusion. If you're still confused, don't worry. I don't know if this showed up on my exam. It might have, but Rosemary threw it in here just in case. She definitely has a lot more experience with past exams than I do, so. But there you go, stereoisomers. If you have any questions still on this, feel free to email either of us. I will pull up more examples of like just stereoisomers in general, and then maybe that can help clarify some things. All right, I'm going to let you guys take a screenshot of this page before I move on. There we go. So go ahead and take a screenshot. All right, so let's go ahead and move on to the next page. Ooh, I scrolled too much. All right, that should be all of them for that page. And I'm going to go ahead. All right, so we are talking about this reaction here. So basically it is saying that we produce this compound. And the way that we produce this compound is by reacting something with an excess of benzaldehyde. So please do remember what a benzaldehyde looks like. You can't just kind of think of it as a benzene with an aldehyde, because that's literally what it is. So we're asking, what did we react this with to create this? So notice this is a phenyl, that's a phenyl, then we have the carbon with a hydrogen, carbon with a hydrogen. If you guys can't see it already, this was our aldehyde, and here's that double bond for the oxygens. So just kind of looking at what we were dealing with here, remember what happened when we saw that we had an excess of the starting product? What was that other thing that we reacted it with, that we know if we had excess of this, we can end up putting it together like that? That was kind of a really crappy way to word that, but hopefully you guys are kind of getting what I'm getting at here. And if you guys said hydrazine, you are right. So let me refer back. So remember for this guy here, our hydrazone with excess, see how we had the hydrazine here? We had excess of our starting product, and then we reacted it once, and this is what we ended up with. We reacted it with it again, and then we formed another one of these, but upside down. And that is what we were doing here. We started out with the benzaldehyde. We had excess of this benzaldehyde. So basically, our first product ended up being this, a nitrogen with a NH2. And then we reacted it again. Let me scoot this guy over. So when we reacted again, we formed this guy, a nitrogen here, bonded to another nitrogen, and it's basically this group, but sideways. So let me move this and try my best to draw this. Let's see. How do I draw this properly? That is the best drawing you guys are going to get from me. But yeah, hopefully you guys can see it now. But yes, it is hydrazone. So remember, this is the one where we're going to be dealing with things in excess. So typically if you see something with excess, it's usually going to be like a hydrazone thing. But yeah. So that is the answer for 52. Let's go ahead. Number 70. Very famous Dr. West type style questions where we do multi-synthesis reactions. Although he did say he's not going to throw Grignard on this exam, I believe. So I don't really think you need to know this one, but we can do it just in case you do need to know it. So what are we dealing with here? If you said a Friedel-Crafts alkylation, acylation, you are right. Because notice that oxygen there. So if you ever want to tell the difference between a Friedel-Crafts alkylation and an acylation, if you see that there's an oxygen, it's going to be an acylation. If you do not see that there's an oxygen there and it's just a bunch of CHs and then a Cl, it's going to be an alkylation. Quick little shortcut if you guys did not notice that by now. So here's our benzene. We're reacting it with this guy, so we end up with CH3. We end up with this as our start. So now we are going to be reacting it with a Grignard reagent. So remember, Grignard can act as an acid or a base. Once again, guys, please don't worry about this one too much because I believe he said he's not going to put this on there. But, he might. I really don't think he will because he said he won't. But just in case, we're going to go through this anyways. So remember, Grignard can act as an acid or a base. So this guy, what it's going to do, it's going to come in, attack here. We're going to pop this guy up. Good old Grignard doing its thing. So I will draw the Grignard reagent in like this. So we have the CH and this, we added on the methyl. And this guy is now this. And then we're reacting it with H3O+. And all that guy is going to do is protonate this guy here. So we will end up boop, 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 boop. With this. So now we just need to see which one of these answer choices looks like that. And the one that looks like that is B. All right, I'm going to let you guys take a minute to let that in. Well, soak that in. Okay, so hopefully you guys took that in okay. Next, we are going to be doing something. I will teach you guys a neat little trick for this guy. All right, so you see this P right here, and then you see the C6H5 So C6H5 is a phenyl, remember? So this guy is just PH3P. And what is that, guys? That is a part of the illid. Rosemary has finally taught me how to say it. I always called it an ild. I don't know why, but it's like an illid. So when you see this and then you see this, I basically skip those steps and I realized this. We can just cut into Rosemary's shortcut method without having to draw everything out. And the way you could do that shortcut method is this. So this is the carbonyl that we're reacting it with. All you have to do, cut off the head like she said, throw it in a bucket. And then all you're going to do from the starting product over here, that is going to form the illid. So if you guys need to know, G, at step G, we will form the illid. All you have to do is take this starting product, pretend this was that double bonded head, and cut off the BR. Then all you're going to do is take those body parts and stick it onto that double bond. So I will draw these in two different colors. This is going to be our carbonyl, and then I'm going to put our illid in this color. We have a CH2, C6H5. So that is what we should end up with for this. So we could go ahead and look at our answer choices. So we know that A isn't right because there's no double bonds. B could be right. C doesn't make sense because we have two double bonds. Why would we have two double bonds? D could also be right, and E could also be right. So we need to look at these guys carefully. So now we're stuck between B, D, and E. So let's look at B. Does B make any sense when we have this double bonded oxygen still here? No, it does not. So we can rule out B. So now we're stuck between D and E. So let's look. We had a C6H5 and a CH3, a C6H5C CH3 on one side of the double bond. So let's see. This guy doesn't make sense because notice how we do not have a CH3 on this side anymore. We have a C6H5 a CH2, and a CH. And on the other side, we have a CH, C6H5. Does that make any sense? Based on what we did over here? No, it does not. So that means E is our answer. All right. That was a little confusing. Don't worry, I will try and explain it another way. So I know this one doesn't have that extra hydrogen. I forgot to mention that step. You do have to erase the hydrogen from it. So it might help if I drew this out. Okay. So if I were to draw our ylid, here's our C6H5, and then the ylid is going to be forming here. So the PPH3. So notice how one hydrogen got taken away, because what does this guy do? It takes away a hydrogen. So if you guys want me to show you the steps for this, let me erase this. F from these two reacting with each other will form C6H5, CH2, and then we will have the PH3 here with a positive charge. After we have this, we have the C6H5Li. All that guy is going to do is take off one of the hydrogens, and now we will end up with this as our ylid. So now when we do this reaction, we are now reacting it with this guy, the C6H5CCH3, double bond oxygen. Now we can do the rosemary method. Cleave the head, throw them in buckets. So then we end up with C6H5CH, double bond. We're going to paste it with the other guy, CCH3, H5, C6. This is what we end up with, and as you can see, that is exactly what E is. They just split it up a little weird, so they kept the CCH3 in one line, and then this carbon has the phenyl ring bonded to it, which technically is right over here. Don't let it stress you out, guys. Just kind of look at what is bonded to the carbons that are part of the double bond, and then you'll figure it out, I promise. But if you didn't get that question, go ahead and go over it a couple more times. We do have a couple more of those questions in here. But feel free to pause the video and try it. Okay, so let's go ahead and go into 82 and 84. All right, 84 is the one that always gets everybody tripped up. So we are definitely doing 84. That was on my exam when I took this class. You guys didn't hear me say that, but it has popped up in the past. All right, so let's go ahead and start with 82. If my iPad wants to zoom, oh, too zoomed, okay. And now we're stuck like this. There we go. So once again, guys, these two are just saying that we're forming the ylid. So our creation after here is the CH3 bonded to the PPH3. Remember, this guy here is just a phenyl. They always write it out as C6H5, which confused the poop out of me before. So then we have this guy here. And remember, it just takes away a hydrogen. So instead of CH3, we now have a CH2 and a double bonded PPH3. So now let's, there we go. Let us now take the C6H5CCH3. I totally forgot a carbon, which is fine. CCH3. And now, chop off the heads, throw them in buckets. And now we form, I totally ran out of room. I will draw it down here. C6H5CCH3. Here's our double bond, and then we paste on our CH2. So now we just need to see which one of these looks like that. Let's start with A. So we have a CH2 on one side. That's good, CH2. And then on the carbon, we have a CH3 and then a phenyl. CH3 and then a phenyl. Cool. There we go. There's our answer. This one is A. But if you guys ever want to do the shortcut method, even shorter than drawing this part out, I don't want to confuse the crap out of everybody, but I'm going to try and show you guys. Cleave off the head, cut off the eye, we'll cut off the halogen, and then subtract one hydrogen. Take this and paste it where it was over here. So then, C6, H5, C, CH3, double bond, paste on the CH2. And then you could skip over the steps of making the ylid. But if that doesn't work for you guys, no big deal. Do it the other way, perfectly fine, whatever gets you guys the right answer. So I'm going to erase this just in case, because I don't want to confuse everybody. So, and my iPad's frozen, which is fine. I'm fine. Okay. So now this one is asking, what is the reactant W in the synthesis given below? This seems very daunting, guys. I promise you it's not daunting at all. All right. This guy says Witting reagent, right? So we know this is the Witting product. You don't need to know what the Witting product is called. You could literally just call it a Witting product. So this guy here is a Witting product. So we know we take the ylid and then a carbonyl to form the product, right? They give you the carbonyl. So this is our carbonyl. So when we are doing a retrosynthesis, which is what this is because we're trying to figure out what W is, we need to find where this carbonyl is in our Witting product. And the easiest way to do that is to split this molecule at its double bond. Because remember, we copy and paste the double bonds on top of each other. So, go ahead and split this guy in half. Notice how this guy on the right is literally our carbonyl. It's just drawn a little bit differently. So we have an ethyl here, ethyl here, ethyl here, ethyl here, double bond, double bond. So there's our carbonyl. So if we know that is our carbonyl, we know that this side needed to come from the ylid, right? So if I were to draw the ylid, I'm going to draw an arrow going this way. Let me do this in a different color. We know our ylid kind of looks like this. So remember where that double bond was? The head of this guy was a PPH3. So that is what our Witting reagent was. So let me label this guy our Witting reagent. But the question is not asking for our Witting reagent. It is asking for W, which is before we form our Witting reagent. I know this is a lot, but I promise it's not as bad as it seems. So now we take this Witting reagent, and all you have to do is take this guy here, and then we turn it into something that could be treated with the PPH3. So all this guy was a cyclopentane, and then it had something here, which is typically a halogen. So let me just make this an X, really. Because remember that what we start with to form the ylid is some type of alkyl halide, and then we react it with the PPH3, and then we take off a hydrogen with the C6H5Li, and that is how we form our Wittig reagent. So in case you guys aren't exactly following, let me pull this up and show you guys here. So we started out with this alkyl halide. This is our alkyl halide that we're drawing over here. Then we react this alkyl halide with this PPH3, and then we will end up forming this guy here. So now we have formed our Wittig reagent. So we now know that this guy needs to be a group, a cyclopentane with some form of halogen. I'm sorry this is a really long-winded explanation, but I don't want you guys to get this wrong. So this has a ketone, right? That is not a halogen. This one is an alkene. Which once again is not a halogen. This guy has an ol, meaning we have an alcohol. So this is also not it. The triphenylphosphine oxide is what we're talking about when we form the PPH3 double bonded to the oxygen. That is what our leftover product is if we were to draw that out from the Wittig reaction. So the byproduct of this was the PPH3. I drew it wrong. Double bonded to the oxygen. So this guy is also not it. D is it because we have the halogen of a bromo, and then we have our cyclopentane. So please, please, guys, do not get this wrong on the exam. I know that was really, really long-winded, but I promise you, the Wittig reaction is not as bad as it seems. Just go backwards, cut it in half, find the side that you're looking for. We found that this side was the carbonyl, so then we knew this side needed to be the ylid. So here is our ylid. And then we went one step back and then turned it into a halogen. Okay, I'm going to zoom out on this page and then we will do the next ones. We are almost done. I think we only have like 8 more questions. That's what it looks like. Okay. So onwards we go. So it is asking, what is the general order of decreasing reactivity of these carbonyl compounds towards nucleophilic reagents? So we want decreasing reactivity. So remember when we are doing these, the most reactive is going to be the one that is the least stable when we take off one of the groups. So this guy here looks like this. It is a formaldehyde, in case you didn't know that. This guy here is simply a ketone. This one here is a aldehyde. This guy has a chicken foot on one side. This guy has a chicken foot on both sides. So, out of all of these, which one do you guys think is going to be the most reactive? If you guys said 4, you are totally right. So go ahead and look at the answer choices and mark off anything that doesn't start with 4. And when you do that, we end up with B as the answer. I don't know if I let you guys take a screenshot of this page. I always forget to do that. I'm going to let you guys take a screenshot now. I'm sorry. But yes, remember, this guy is going to be our most reactive, because if we took off one of these hydrogens, this guy is going to be super freaking unstable. So that is why it's going to be our most reactive. And then we'll come to, because this is an aldehyde, so if we took off this hydrogen, it will be unstable, but not as unstable as this guy, because at least it has a CH3. Then will come our ketone, because we have one CH3 left over. If we popped off a hydrogen, we would have a CH2, and then so on and so forth. Okay, so now it is asking which of these gem diols is expected to be the most stable. We're already given that all of these guys are going to be gem diols. So what we're really looking for here is, so we have a boop, boop. We have 2 OHs here, and then we have fluorines on all of these guys. this guy here, I'm going to draw it out this way. Then we have this guy. Then we have this one. Sorry guys, I feel like it's easier to visualize when it's drawn out. I don't know if it's just me, but for all my visual learners, this is how I have to do it. So don't feel bad if you have to draw it out too. You're not alone. And then finally this guy, which is a Cl, CH2, C, OH, OH. All right. So the one that is going to be the most stable, take a second and think about it. The answer for this is A, because notice how we have all these fluorines on here? This one's going to be exceptionally stable because if we popped off one of these guys, we're still going to be able to have all these fluorines here and these OHs. This guy, if we popped off one of these things, we only have OHs. This one is like, we have CH3s on both sides. This one we have the ring, which is pretty stable, you know, we do like to see the ring there. And then this guy here just has the Cl. But basically, since this guy has so many electronegative fluorines, it's going to be able to basically hold the charge and be okay. Mainly okay. The most stable out of all of them. The other ones, they'll kind of freak out a little bit and probably do something crazy. Alright. So, on the flip side, I really don't want to draw out all these molecules again, so I'm going to copy and paste them. Duplicate. And bam. I think that'll look good. Just like that. Okay. So, which one of these do you think would be the least stable? So, we already know that this one is the most stable. So, out of the 4 that we have left, which one do you think is going to be the least stable? Basically, look at which one, if we kind of looked at this the way that we did for these guys up here, for these carbonyl compounds, we can kind of apply the same thing to the gem dials. So just imagine this was a double bonded oxygen. And like one of these guys was a double bonded oxygen. Which one would probably be the least stable? If you said C, you are totally right, because if we replace this with a double bonded oxygen, we would just be left with a ketone. And the ketone doesn't really like, you know, being super stable. It'll probably do something. Unlike the rest of them. Okay. So that is why C is the answer for this guy. Alright. So, I'm going to zoom out, let you guys take a screenshot of this page. And we will, basically, I think we only have 2 more pages. 3 more pages, I lied. Or maybe 2 more. Alright, I'm going to scroll. Yeah, only 2 more pages. So, I'm going to let you guys take a screenshot. I'm not going to mess it up this time. Alright. So, 143. It kind of looks like the one we just did on the other page, but notice the key word. It says increasing reactivity. So, we want the least reactive to the most reactive. So, we already said, let me grab these guys. This is our most reactive. So if you want to go based on that, we could kind of look at all of them and see which one gives us 4 as our last one. So we're looking at this column. B is not it, E is not it. So now we're stuck between A, C, and D. So if you guys want, you can go ahead and see which one is going to be the least reactive. So remember, this guy had 2 sets of these chicken feet. And this guy only had 1 set of the chicken feet. So we're between these 2. Which one do we think is going to be more stable or less reactive? The one with 1 chicken foot or 2 chicken foot? 2 chicken feet. If you said 2 chicken feet, you are right. So this guy here is going to be our most reactive. So, because of that, we know that it's this one, because none of the other ones starts with 5. Alright. So, this one is asking which of the following compounds is an acetal. So remember what an acetal looks like. An acetal starts out as an aldehyde, and then it turns into an acetal. So, let's look at these. This guy here, do we see anything that could possibly, let's start out with this guy. Do we see anything that could possibly indicate that this is an acetal? So if you guys don't remember what an acetal looks like, this is our basic acetal. See how it's saying acetal and not a hemiacetal? So it does mean we will have both R groups substituted on. This one, not really. We have 2 of these carbonyl oxygens, so I would say no to 1. This guy here, we have a like ester going on one side and then a carboxylic acid on the other, so that is also not it. So now we're stuck between 3 and 4. 4 kind of looks like it, but do we see anything that would really give us the acetal of this hydrogen? No, we kind of don't. So our answer is 3. I will try and show you guys how you could find the hydrogen from this. So if we looked at this compound, let me move this guy this way a little bit. So let's kind of look at it zoomed in. So we could indicate this as one of our R groups, and then this side as another R group. So I would kind of split it like this. R group, R group. That was a horrible way to split it. But basically, this is its R group, which we saw here. We need to have an R group bonded to the oxygen. So that means the carbon that it's bonded to needs to have a hydrogen present. This one has a hydrogen right here. That hydrogen, remember, it's only one hydrogen. Just one hydrogen. We don't want 2 hydrogens. This guy would have 2 hydrogens, and this guy would have 2 hydrogens. And the ends would have 3. This guy only has 1, so that is where the H is hiding from our aldehyde. So oxygen, oxygen, carbon, hydrogen from that carbon, and then a CH3. So that is going to be our acetal. All right. So then ethyl acetal is kind of weird. So it's going to be an acetal, but it's going to have a thio group. So a thioacetal basically looks like this. R group, and then it's going to have this weird like SS. Something along the lines of this. This is kind of what a thioacetal looks like. So it's going to have these 2 S groups on there. So the answer to this is D. So basically, instead of having on those 2 R groups, the 2 oxygens, so instead of having R, O, R, O, R, my bad, this is an acetal, so let me switch this to hydrogen. So instead of having these ORs, we are actually going to have SR groups, so we just replace these guys with S's. And that, my friends, is what a thioacetal looks like. And this is supposed to be a hydrogen. I don't know why I didn't switch it. So basically, the only difference between a acetal and a thioacetal is that the O's are swapped for S's, which is what you see here. This guy still has an OR, so we know that's not it. This guy here has an SH, which doesn't make sense. This one still has an OH, so that's not it. And then this guy here is simply, for some reason, this, which is not what we do when we're forming an acetal. So this is what a thioacetal looks like. I'm going to go ahead, zoom out, give you guys a chance to screenshot this, and then we will move on to, I think, our last page. Okay. All right, so this is our last page. Once again, we are doing more of the identifying which one's an acetal, and so on. All right, So this guy, 116, is asking for an acetal. So remember acetal. Once again, H, an R group, O, R group, O, R group, because we are not asking for a hemiacetal. So let's look at this guy here. These guys are kind of bonded way too far apart from each other, because notice how our oxygens are bonded to the same carbon. These ones aren't. They are bonded on two different oxygens, so that one's not it. I mean, two different carbons, my bad. This guy also can't be it, because once again, they're not really conjoining at one carbon. They are very much far apart. So this one is not it. So now we're stuck between 1 and 2. So 1 shows us that we have these two oxygens coming together at a carbon, and that carbon does have a hydrogen. So this guy is pretty good so far. But notice how this guy has an OH. That OH is not an OR group. So this one is not our answer. This one also has a hydrogen in the same spot, but instead we have an OCH3 group. Since that is a OR group, that is going to be our answer. So the answer for this one is 2. So remember, we're looking for an acetal, so we should not have any OHs. We should only have an OR group. All right, and then to combat that, now we are looking for the hemiacetal. Hemiacetal is this. So we will have an OR group and an OH group, because remember, it is a hemiacetal, so you kind of think of it like halfway. So we need to find one that has an OH group. We already know these two didn't make sense. And then we saw that this one has a hydrogen and this one has a hydrogen. So in reverse to the other one, we do not want to have both OR groups. We only want one OR group. So this one is not our answer, and that leaves us with A. And A is it because we have one OH, one OR group, and then the hydrogen for the aldehyde. All right, last one, guys. So 148. Holy crap, I never thought we'd get here. So it's asking which of the following is formed when 3-methylcyclopentanone reacts with hydroxylamine. That was a mouthful. So let's go ahead and draw out our molecule. All right, so we know we have a cyclopentane, and then I'm going to put my ketone over here for no apparent reason, just because that's how I see all their double bonds, so I decided to draw it like they did. All right, so then we are going to bond our methyl over here, because this is 1,3, 1, 2, 3. So now we are reacting this with a hydroxylamine. So what does our hydroxylamine look like, guys? It is a NH2 group bonded to an OH. All right, I will show you guys my copy-paste method. If it doesn't work for you, or if you can't visualize it, no big deal, but I will show you guys anyways. So, first step, cut off the head of the double bond. Throw it in the garbage. Then, take the nitrogen, not the OH, take the nitrogen and take off all of its hydrogens. So, scribble out its hydrogens. Then, take whatever's left of both and paste on what we have left over. So notice how we only have the NOH, and then we still have our cyclopentane, but instead of having this, we added on this group where the double bond was. And so the answer for this guy, as you guys can see, is going to be 3. I don't know why I chose to highlight it in that color, but I did. And the answer is C. All right. Hopefully that makes sense for you guys. If you guys did like the copy and paste method, I posted it on my Canvas page. I did it for my last SI session. So you guys should have access to it underneath files. So if you like that method, I did it for basically all of them except for 2. So you can go ahead and look over there. But that is it, everybody. We have officially finished all the practice problems. So I hope you enjoyed, And I wish you guys the best of luck on your exam either tomorrow or on Friday. You guys got this. You guys have gone through these so many times, and I have 100% faith in you guys. You guys are going to crush it. All right, I'm going to stop sharing and end the recording. Bye, guys.